A similar problem to the first one. We're given a collection of candidates, and these are always going to be positive numbers, and we're given a positive target number that we want to sum up to. And there could be multiple combinations from the candidates that can sum up to this target number. So we want to find all unique combinations that sum up to the target. Also, each number from candidates can only be used up to one time. So it's not like it's unbounded, right? We don't have an infinite supply of each one. And the solution set cannot contain duplicates. So this is what's actually going to make this problem a little bit tricky, because take a look at the input, right? So we want to sum up to target A.
也会不加班吗？我感觉只要在国内就会加班。
Meaning we skip 10, right? Then next we do the same thing for 1. Include 1 or skip 1. Over here, include 1 or skip 1, right? So we'd have one combination 10, 1. Okay, over here I was supposed to skip 1. So over here we'll take 1, over here we skip 1. So here we have a combination 10, 1, just 10, or just 1, or nothing, right? So we're looking for all combinations. We can enumerate it like that, but the problem we're going to notice if we do it like this is we're going to end up with duplicate combinations. So let me try to explain how we can do it without duplicate combinations. By the way, no matter how we do it, since we do actually have to create all the combinations, the time complexity overall is going to be 2 to the power of n, because that's how many combinations we can have for each value. We can choose to include it or not include it. N is going to be the size of the input candidates. So let's take a look at this example input array, and let's say we're trying to sum up to target 8. So let's just start back with that previous decision tree I was on. So let's try it number by number, and let's see why this doesn't work. So we can choose to include 10 or choose not to include 10, right? Basically skip 10. Now notice how already when we choose 10, we actually went over the target, right? So none of the paths in this left tree, the decision tree, are ever going to be equal to the target, because all of these numbers are positive. We're always going to be greater than the value, the target value 8. So this basically stops. So we can choose not to continue down that way. Now from here, we can choose to include 1 or skip 1. And then, so then, that takes care of 1. Then next we get to 2. So from here, we can choose to include 2 or skip 2. Here, include 2. Where we didn't choose anything here, or skip 2, where we will still have nothing over here. And then basically keep doing that until we ever get to a sum where the target or the sum total is equal to the target. So now we can do the same thing with 7, include 7 or skip 7. Similarly over here, include 7 or skip 7. Here we can also include 7, but notice how if we do that, then we get a sum of 9. That was too big, right? So this path is not going to lead to a solution. Here we also got to, I think, 10, so we cannot find the sum 8. This, though, is going to be a possible solution, 1, 7. This so far is too small, but basically now what I'm getting at, you probably get the main idea here, but what I'm getting at is this is not going to work because this is going to lead to duplicates. Let me show you why. So here we can include 7 or skip 7. And now, so we're going to do the same thing with 6, right? Let me just skip 6 for now and just show you what happens with the 1. So we can include 1 or skip 1, but notice how this path over here is also 7, 1, right? And this path is also 1, 7. So it's the same path, right? It's basically the same sum. So we ended up with a duplicate. How can we ignore duplicates? Well, first of all, let me explain the logic of how we're going to go about it, and then I'm going to show you the actual algorithm. So initially our problem is we want to sum to the target 8, right? So this is what we're trying to look for. So we can think of it in two different ways, right? One decision is going to be where we include a 1 value, right, for this subproblem 8, because notice how we have multiple 1s. That's kind of where the problem comes from. That's how we end up getting duplicates. So one path, well, we will include 1s, and in another path, we're not going to include any 1s for the subproblem 8, right? So by doing that, by saying, okay, this left subtree is definitely going to contain a 1, this right subtree is not going to contain any 1s at all, we can guarantee that both of these are going to lead to different combinations, right? I think that is kind of obvious. This contains a 1, this will never contain a 1, so they're always going to be different combinations. And similarly, it's basically a recursive definition. So next we'll get to the subproblem 7, right? We're trying to sum up to 7 over here because we already have a 1, so now we just want to sum up to 7. Again, what we're going to say is, okay, left subtree could include a 1, and right subtree is never going to contain a 1. So the left subtree definitely has a 1, the right subtree never has a 1. So by definition, this path is always going to be different than this path. They're always going to lead to different combinations. So that's kind of the main logic we're going to follow. Let me show you how we're actually going to implement that. Since we're going to be doing this recursively, as I just kind of mentioned that it's a recursive definition, one thing that's going to be easy for us to keep track is, one, we're going to have a pointer I, which is going to tell us what position we're at so far, and we can only choose elements that are equal to I or to the right of I. And so, what we're trying to do is say, okay, in one path, we're including a 1, and later we're going to say, the other path is basically we're not including any 1s. So it would be easy for us if we sorted the input array, because if we sorted it, this is kind of what it would look like. It would look 1, 1. So this is if we sorted the array. So then if our pointer I is at this 1, we can say, okay, one path is including this 1, in which case, the subproblem will become I plus 1. We're then looking at the remaining portion of the array. If we decide not to include any 1s at all, our I pointer is over here. We're saying we're going to skip this one and this one. We're skipping all of the 1s. We're basically saying we're going to shift I all the way to the point where we have reached a different element, because now if our pointer I is over here, we can choose from any of these values, and we guarantee that none of these values are ever going to contain the value 1 because the array is sorted, right? So that's mainly the logic that we're going to follow. It's still a brute force solution, so the time complexity is going to be 2 to the power of n, but let me just give you a quick walkthrough of how it's going to work. So initially we have a choice. We can choose 1 or we can skip 1. Let's start with this tree, right? Since we skipped 1, that means we skipped both of the 1s, right? So now we're only going to be able to choose from these values. So next we're at 2. We can choose 2 or skip 2. And since we're skipping 2, we only have a single 2 here. So when we're shifting our I pointer, we only have to shift it by 1, right? Now we have all of these values to choose from, 6, 7, 10. So basically these two subtrees are going to be pretty much identical. So we can either here choose 6 or skip 6. Similarly over here, choose 6 or skip 6, and so on and so on. And you can see that once we choose a 7 over here, basically all of these are going to go over, right? These are going to be too big. These are always going to be greater than 10. You can kind of see how that's going to work out with these candidates. This is a possible solution, 2, 6. But over here, we're going to end up, and once we get to a solution, 2, 6, then we don't want to continue anymore, because then we know if we add positive values, we're always going to exceed the target value. So we found one solution. But over here, if we choose the next value that's available to us, 7, we see that that's actually going to go over 2. 2 plus 7 is going to be 9. That's going to be too big for the target. So we're not going to continue here either. Let's continue on this left subtree. So we included a 1. So now we have a choice of including another 1 or skipping all the 1s altogether, right? So if we include another 1, we'll get something like this, another 1, and then we'll have choices. We can choose a 2 or we can skip 2. And then if we include the next value, it's going to be 6, which is going to end up being too great. Basically, we exceeded the target when we went down this path, so we don't continue. And then over here, we're so far at a sum of 2. We include the next value. We skipped 2 on this path, but we include the next value, 6. So now we found another solution, 1 plus 1 plus 6. And if we chose the other decision, if we choose 7, we're going to end up going over. So we're not going to continue down this path. Let me just save a little bit of space. So next over here, if we skipped the 1, we could have gotten a 2, and then we would have gotten a 6, 7, or 10, and that also would have been too great. Right, but we also could have skipped the 2 as well, and if we skipped the 2, we could have gotten a 7, and this is also another solution. So we found 3 different solutions, right? So we found 3 different solutions, 1, 7, 2, 6, and 1, 1, 6. I think that's all 3 of the solutions, and you can kind of see how doing it this way ended up eliminating the duplicates, right? We either chose a 1, in which case we could have chosen any of the elements, or we skipped 1, and we skipped both of the ones, and then we could have only chosen these. So with that being said, we can now actually dive into the code. It's a little bit tricky, but I'll guide you through it. Let's get into the code now. And remember, the first thing that we wanted to do is actually sort our input array candidates. That's going to make it easy for us to eliminate the duplicates. And we're going to be maintaining a result, which is going to be basically the combinations that we're returning. And we're going to be doing this with backtracking. It's recursive. And we're basically just doing the brute force. So we're going to have 3 variables. Cur is going to be basically we're maintaining the current combination. And another variable is going to be I, the index that we're at in our candidates array. And lastly is going to be the current target that we're trying to sum up to, because every time we add a candidate, we're basically decreasing the target that we're trying to sum up to. So if this target ends up becoming 0, that means we've reached the base case, we've found the solution. In that case, what can we do? Well, we want to update our result, right? To the result, we're going to append what the current combination is, but we're going to make a copy of the current combination because this is kind of a variable that we're passing around. We're going to still be updating this current value, and when we append it, we want to append a copy. We don't want to append the original array itself because that's a reference. We want to make a copy before we add it to the result. Another base case is going to be if the target is greater than 0, or even if it's equal to 0, either case, we want to end up returning. So basically, if the target was equal to 0, we would execute this statement, and then after we would return. If it wasn't equal to 0, but it was greater, or actually, I should say less than 0, that means we went negative, then we want to return anyway. So next, we want to go through every single candidate in the input, right? We want to consider each one the first value. And what are we going to do with this candidate? Well, we're going to append it to the current combination, right? And this is basically the pre-work before we actually call the backtracking function once again. So now we're going to be going recursive, right? We updated our current combination. We're going to send the current into this function. We're also going to say I plus 1 because we're saying that we can choose any of the remaining candidates. And we're going to say the target is now going to be equal to itself minus this candidate that we just ended up choosing. And after we finish that recursive call, we want to do a little bit of cleanup. So we want to basically remove the current candidate that we just ended up adding to the combination. But don't forget, remember what I was saying. So if we chose a candidate such as 1, then on the next iteration of the loop, we don't want to end up choosing that same candidate twice, right? We want to make a branch. We want to say, okay, we can choose this candidate. We already chose one decision where we end up adding that candidate 1. The next time we want to skip 1. So how can we do that? Well, we can say, okay, if this candidate is equal to the previous candidate that we just chose, then we want to skip this iteration of the loop. So then we have to maintain what that previous candidate was. So over here, we can say, okay, previous is now going to be the current candidate that we just chose so that we can use this variable in the next iteration of the loop. But we still have to initialize this with something outside of the loops. So the default value I'm just going to give it is -1 because none of the candidates are going to be -1. So this if statement will never execute as being true on the first iteration, which is what we want it to do. And so that actually is the entire recursive function. We're just brute forcing it. There's just a little bit of logic. You have to do a little bit of cleanup, and basically this previous variable is what eliminates the duplicates for us. So after that, all we have to do is call the backtracking function, passing in an empty array for the initial combination. That makes sense. Starting at index 0, that makes sense. And the target value that we want to sum up to is the target value that we're given in the input. That also makes sense. Once we're done with that, we can just return the result that we updated and added all the combinations to from this line over here. Oops, for some reason, and this candidate is candidate of index I. I always forget. And it has an S at the end. And down here, I also called it candidate. You can tell that I'm pretty sleepy right now, but hopefully those are all the typos that I had. Oh, and lastly, when we're actually taking our index I, we don't want to necessarily go through all the indices. That's why we're passing in this I value in the input backtrack. So actually, instead of calling this I, since we're actually using a different variable for I here, I'm going to call this I position, basically the starting position that we're starting at when we call the recursive function. So from here, instead of saying for I in range of the entire candidates, we actually want to start at this starting position and then go to the end of candidates. So that's going to be the actual solution. Sorry about all the bugs and typos. But as you can see, this solution actually does work and it is pretty efficient. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching. and typos. But as you can see, this